Right, so we'll continue today with Thomas Bodin, who's your professor, I guess. Yeah, you are a professor.
Researcher, yeah.
Researcher, yeah, at the University of Lyon and on transdimensional inverse. Inference.
Thank you. Thank you very much for the invitation. And so, yes, I'm going to talk about the work that we've been doing with Malcolm Sambridge over the last 10 years. And the title of the work is Transdimensional Inference in the Geosciences. And so transdimensional means across dimensions, where the dimension of the model space is variable. So the dimension of the model space is the number of model parameters, the number of unknowns. So we want to let the parametrization or the number of unknowns to be a variable. So another title that I could have used is when one of the things you don't know is the number of things you don't know. And so this is the problem I'd like to talk about today. So I will start with a very simple cartoon showing a classical inverse problem in geophysics. So we have the Earth, we have stations at the surface of the Earth, and we might measure geophysical data, and we want to recover a model of the Earth, here with 4 parameters, 4 unknown parameters, x1, x2, x3, and x4. And so we have a simple inverse problem. But the thing here is that we have defined in advance as users that we want to recover 4 unknown parameters. But equally well, we could have chosen to invert for 2 parameters or for 6 parameters. And this is a choice that we make and that defines very much the solution. The solution to our problem, the model of the Earth that we are going to recover, depends very much on these assumptions that are very arbitrary. So how do we choose the number of parameters? And so this is exactly the question that Alison was talking about when she was showing that you can put a lot of small spheres at the surface when you invert gravity data. And you can put as many spheres as you want. You can fit the data perfectly. The question really is how much information is in the data and how much information should I put in the model? And I don't want to put too much information in the model. So you see, those are different parametrizations, spatial parametrizations, but the problem is the same if you ask how many physical parameters do I want to invert for in each layer. For example, in seismology, we like to invert for the velocity of seismic waves. So we can say, okay, we're going to try to recover the VS, the shear wave velocity. But we can be also a bit more ambitious and say, okay, let's try to also invert for anisotropy. We add an extra parameter, an extra degree of freedom. And we can even be more ambitious and say, okay, let's also try to invert for attenuation. We can always go and add more parameters. We could also try to recover the anisotropy of attenuation if we wanted, right? So yeah, how much can we resolve? How much can we really resolve? So this is really the problem that I'd like to talk about today. And it's very funny because I talked to Klaus in the bus when we were coming, and there is actually a paper that Klaus and Albert Tarantola wrote in '95. And it's a paper on the Monte Carlo sampling. It's a great paper. There is a lot of things. It's called Monte Carlo sampling of solutions to inverse problems. And in this paper, there is a section where they actually let the parametrization be a variable. The parametrization, the number of layers, is a variable. So here, what they did, they were sampling with a Monte Carlo, Markov chain Monte Carlo algorithm. They were sampling a lot of different models. And in the sampling process, they were adding layers and removing layers. So the number of layers was a variable. The number of unknowns in the problem was a variable. So in '95, in this paper, Klaus and Albert were already addressing this issue. And so all the work that we've been working on comes from this. So what I'm going to say is that I'm going to start with a general introduction about this issue of the parametrization in seismic tomography. And then I'll show how with different examples, how we can address these issues with this transdimensional inversions. So okay, so let's start with the parametrization issues. And for that, I'm going to use again the classical travel time tomographic problem that we have seen a lot of times already. So here we have, this is a 2D tomography. We have sources at the surface of the Earth. We have stations, and we have surface waves that propagate from sources to receivers. Our data, there are travel times. The travel time that the surface wave takes to travel from a source to a receiver. So we have a travel time. That's our data. The travel time, we also know the distance between the source and the station. So from the travel time and the distance, you can derive a velocity. So what we actually observe is a velocity along a ray, an integrated velocity. It's the average velocity along a ray between a source and a station. And of course, we don't know if the wave was going fast at the beginning and slow at the end. The only thing that we know is the average velocity. So we have a lot of average velocities along rays, and we want to reconstruct a continuous field of a local velocity. And we have only a discrete number of average velocities. And we want to reconstruct a continuous field. So there is a problem. We have to discretize this continuous field that we want to recover. We can only recover a discrete set of parameters. So here are two classical choices. We can decide to parameterize our model here with different cells, square cells. And then the problem is quite simple. From a set of average velocities along rays, we want to recover a set of average velocities within cells, right? And so we are not going to recover the full velocity field. We are only going to recover average velocities within cells. And then there is the question of the parametrization. How do we parameterize the model? Should we use a fine grid or coarse grid? And if we use a coarse grid, you see that there is a lot of rays going through one cell. So the average velocity within this cell is going to be a very good average, a very robust average. The uncertainty on this average is going to be quite small. So we have a good constraint on the model. But in the same time, the resolution is quite bad because we have a large cells. And here on the right is the opposite. We have small cells, so we have a good resolution, but you see that there are some cells where you just have one ray that is crossing. Maybe there is, here a cell where you don't have any rays that are crossing. So we have a good resolution, but the uncertainties on the model parameters are very high. So we have this trade-off, and the solution depends very much on the choice that we make. And so we'd like to have a model of the Earth that represents the information contained in the data, but actually is going to represent the information that is in the data and the choices that we make. And this is a big problem. So very often in seismology, in seismic imaging, we choose the solution on the right. We over-parameterize the model, so we lack information, because we want a good resolution, but we have a bad constraint on the model. We have large uncertainties, and we lack information on the model. So what we do is we need to add extra information about the model parameters. We don't know exactly we don't know at all what's the velocity in this cell because there is no rays that are crossing. So we need to add extra non-data driven information. And we do that through regularization, and we've been talking about that, smoothing, damping, because we want to, the uncertainties are large and we want to reduce the uncertainties, and we can reduce artificially these uncertainties by adding information that is not contained in the data with regularization. And as soon as we regularize, a big problem is that we lose the ability to propagate errors from the data towards errors in the model. So if we are going to add extra information with regularization, we won't be anymore able to look at uncertainties here. They will be artificially small, and this is a big problem. We know how to stabilize the problem, but we lose the ability to quantify uncertainties. Okay, so here I'd like to show you a couple of examples of when this happens in seismology. And this is a first example with global seismology. This is a global map of surface wave velocities. And we have two maps that are obtained with exactly the same data set, but with different parametrizations. And there is no way to quantify uncertainties here. There is no way to say this one is better or than this one, because we lost the ability to quantify uncertainties. And so we might be very interested in the small details, maybe somewhere, because we have a geological question and we may want to interpret things there. But maybe here we don't know. Maybe we would be interpreting noise in the data. So that's a big problem. So this is an example where there is no real solution. Another one, so this is a source seismology. This is during the Tohoku Oki earthquake in 2011. From GPS stations in Japan, we can run an inverse problem and try to recover what was the finite slip on the fault. So it's an inversion for slip on the fault. And so here the parametrization is the same, but the smoothing is different. And you see that depending on the level of smoothing that you apply, there is a very, very different solution. Here we have two patches that are rupturing and that are separated. So we have two kind of earthquakes that are happening at the same time. Whereas here it's a big patch that is slipping alone. So here again, so the story that you make is going to be dependent. So those are ghosts. So the story that you make about your process, the big Tohoku earthquake, is going to be very dependent on the smoothing. A last example, this is travel time tomography below Hawaii in the middle of the Pacific. It's a P-wave travel time, so we have earthquakes, teleseismic events that are coming from very far, and the rays are coming under Hawaii vertically. So we have a lot of vertical rays. That's the geometry of the experiment. And so we have a very good lateral resolution, but the vertical resolution is very poor. And that's why you see a lot of smoothing, vertical smoothing. And this is an effect that we know very well in travel time tomography, is called the smearing. And that's a problem because at the same time we see a smearing, but at the same time we know that there is maybe a plume there and there is a hot spot, and we want to maybe interpret that as a hot material that is coming up. But at the same time, we don't know if it's an artifact from the parametrization, from the smoothing, from the problem. And again, because it's a linearized, regularized inversion, there is no way to quantify whether this is due to smoothing and to quantify uncertainties. Can we really interpret that in terms of a hot material moving up? It's difficult. Yeah. Okay, so those are quite a few examples to show that this is a problem in seismic imaging. And there is a sentence that I like very much that was written by an astrophysicist 20 years ago. When in astrophysics, they started to use, 20 years ago, a lot of modern data inference approaches, and it started really to build up in their community. And Mackenzie said, we use fantastic telescopes, the best physical models and the best computers. But the weak link in this chain is interpreting our data using 100 years old mathematics. And so I think this is a bit what we are facing today, or that we have been facing over the last 10 years in seismology. And those are a bit like the ingredients that Jean-Paul was talking about the first day. In an inverse problem, we have a lot of ingredients. We have data, we need a model, a forward model, and we need an inverse theory. And so in our case, in seismology, the fantastic telescopes that we are using I guess that will be the great arrays that have been deployed in different areas. And for example, there is the US array. So this is an example of a fantastic telescope that we have. And in the US, we have put stations every 70 kilometers. And so here we see the record of the Tohoku earthquake in 2011. We see the waves that are coming from Japan and that are arriving at this array of stations. So red and blue, it's the vertical motion, and you see the little bars, they are the horizontal motions. So we have been able to put stations everywhere on the American continent. And so before we just had stations somewhere, and we were recording the wave field at some stations. But now with array seismology, we have a lot of more data. And for example, here from the wave field, we can compute the spatial gradients, and we can do a lot of new things with these new fantastic telescopes. And Anna also has been recently deploying OBS data. So we have new data, and this is quite useful. Okay, so those will be our fantastic telescopes. And now we also have another ingredient, the best physical models and the best computers. And this is what Stephanie was showing yesterday. This is an example of a spectral element simulation. This is AXIS-M. So we are now able to, from here it's a 1D model, but we can do that on 3D models to compute numerically and very accurately the entire wave field in the Earth. So in blue here you see the P waves, and you see the surface waves, you see the S waves in red, and you see that a lot of reflection of S waves actually makes a surface wave. We don't have to solve normal mode, ray theory, we just solve the entire wave equation on a big computer, and we are able to compute fully the wave field, and this is very useful. So because we have computers and we have good physical models. Okay, so this is our best physical models and best computers. And the last part of the sentence is the weak link in this chain is interpreting our data using 100 years old mathematics. And this is, I've put a picture of Gauss and Newton because we still use Gauss-Newton approaches and steepest ascent approaches to invert our data. And so that's also what was happening 20 years ago in astrophysics when they started to, and Mackenzie here was trying to promote modern data inference approaches. And so that's what he wrote that. So in our case, yeah, we are using, as Andreas was showing on Monday, we are using old mathematics to solve, old optimization frameworks to solve the inverse problem. So here is just a cartoon. It's a bit of a dramatic cartoon because we have an objective function that we want to minimize, the norm of the difference between the data and the estimated data. We want to find the model M that minimizes this function. And what we do is we use the gradient. That's what Andreas was showing. We use the gradient, and we need to start at an initial model. And you see with this cartoon that depending on where you start, you may finish in a very different location because we use derivatives of the data. And we depend very much on an initial model. A very different way to look at that is to say that when we do an inversion, we look at a small perturbation around a reference model. And so the solution depends very much on this reference model. And in global seismology, often we need to fix the crust, the moho, because we were not able to resolve it with long period seismograms. So we fix discontinuities and we solve for a small deviation, a smooth model that is a small deviation around this reference model. But now if you choose to change the reference model, then you get a very different solution. So the solution depends on the crust that you fix, on the reference model that you fix. Okay, so that was a bit of a pessimistic view of seismology, but what I wanted to say that we have three problems. The first one is that images, they depend on choices and they depend on the parametrization that we choose. They depend on the initial model, and regularization prevents from propagating errors. And so the question what I'd like to show is what can we do to address these issues. And so I'm going to try to introduce a bit this idea of transdimensional inversion, where we let the parametrization, the number of unknowns, to be a variable, an unknown in the problem. So the model is not going, the form of the model is not going to be fixed, but is going to be determined by the data. And I'll use, to start with, to introduce this, I will use the most simple inverse problem that we can think about. It's a 1D regression problem, because it's very simple and visual. And so the example I'd like to use is it's a regression problem, and we try to model paleoclimate data. So this is all synthetic. It's a cartoon to kind of explain it's not a cartoon. It's synthetic, but it's a numerical, and the inverse is going to be from real calculations. So, but the problem here is that let's imagine we have paleoclimate data, or that we get from a sedimentologist. That is maybe a proxy of temperature as a function of time or depth. And we want to try to recover a model of the climate on the past. In the past, we want to fit a line through this data, and this data is noisy. So actually, to construct this data, what I've done, I've set up a model in black here with 4 different layers, and I have added a Gaussian noise to this black line. And so this is because in paleoclimatologists, they like to model the past climate with a constant period where the climate was constant, and then abrupt changes. And so the goal is, from the point, can we recover the black line? But most importantly, it's not exactly the black line that we are interested in, is the red, the position of the change points. What is the time in the past where we had the change in the climate? So the question is, if I give you this data set, can you tell me where are the change points? It's a regression problem. It's a very nonlinear regression problem. And also the question is, how many change points do we have? We don't want to say we have 3 change points, where are they? Or we have 4 change points. We don't know in advance the number of change points. So because we don't know the number of change points, the number of unknowns, it becomes a transdimensional problem where the dimension of the model space is variable. And if we apply, we can try to minimize a least square measure and run an optimization algorithm, and this is the most simple thing to do. But you see well here that if we do that, it's not going to work, because of course, if the number of parameters, the number of layers is going to be variable, we can always add more and more and more change points until we fit the data perfectly. Will be actually fitting the noise. It's exactly the same story with the little spheres at the surface when you look at the gravity. You can add more and more and more data until you fit the data perfectly. And so you see that we don't want to overfit the data. We don't want to fit the data over the noise, and that's why the noise here, the sigma, the standard deviation of the data errors, is going to be very, very important. Okay, so an optimization is not going to be a good framework to solve this problem. And that's why what we can do is, instead of an optimization framework, we can use a Bayesian framework. And so here I'm going to try to a bit show how we can derive the Bayesian formulation in a way a bit different from what Andreas showed on Monday. And I will start with this equation. I think everything here starts from here. This is the assumptions that we are going to make. We are going to say the data that we observe is a function of the model plus some random errors. And the errors are going to be random, and here we can assume they are normally distributed, but we can assume other distributions. And so this is a very strong distribution. What I'm saying, again, is that the data is equal to GM, a function of the model, plus some random errors. So that means here my definition of random errors is going to be the difference between DOPS and GM. So my definition of data noise is going to be all the part of the data that I am not able to fit with my model. That's going to be data noise. So it depends, of course, of observational errors, but also if there is errors in G, they will go into the epsilon. If the G is very wrong, if I have a wrong forward theory, I cannot fit the data, then this inability to fit the data because of a wrong forward theory will go into epsilon. And epsilon is a random variable. And here, for example, I'm saying there is no bias. So everything starts here, and here there are a lot of assumptions. But let's say that we are okay with that. So here you see that here M is the Earth, and the Earth is unique. There is only one Earth. The Earth is not a random process. The random variable here is epsilon, the data noise. And so because you have a random variable plus a constant, the observations, the data, they are also a random variable. And we can write the distribution of this random variable. And this distribution is a Gaussian distribution. So I can actually write it. We are in the data space. What's the probability to observe the data for a given model? The model is fixed. The model is the Earth is fixed. And you have, in the data space, a Gaussian function. And sigma is the error in the data. And so here, again, the model is fixed, and the data is the random variable. And so here, this P here, this P is, the meaning of this P is the probability of occurrence of a random process. We have a random process, which is a noise in the data. And because of this random process, we have different realizations of the data. And the P means what's the probability to observe a given realization of the data. So here, this P is the probability of observing a realization of a random process. It's a P in the frequentist view. And now what we can do, I guess that's how I see it, the trick of the Bayesian formulation is to say, now we are going to keep this function, but the D now is going to be fixed, is what we observe, and the random variable, the variable is going to be M. So it's exactly the same, but now I'm plotting exactly the same function, but in the model space. And because we have a G here that is a nonlinear function, then it's not a Gaussian anymore in the model space. We have a complicated function in the model space. And so here we use that to describe our level of knowledge about the M. The D is fixed, and the M represents the Earth. And here, this P here, and that's what I think it was very nice that Andreas on Monday said this P here should not be called a probability of something, because it's not a probability anymore, it's something different. Here we are not using P to describe the probability of occurrence of a random process. We are just using P to describe a level of knowledge on M. We don't know what is M. M can be, we have a knowledge about M, and we use P, a distribution, to represent here what we know about M. But the Earth is not a random process. There is only one temperature field in the Earth. There is only one seismic velocity field on the Earth. It's not a random variable that has different realization. We use here P as a convenient way to describe our level of knowledge about a parameter that we cannot quantify properly. So here we have this distribution, and it depends very much on sigma. Again, sigma is very important. It's the width of this distribution, is the data noise, and we said that the data noise, it's a lot of different things. It's all the part of the data that we cannot explain with our forward model. And what we can do if we don't know the data noise, it's also try to invert for it. And that's the nice way with Bayesian inference. If you don't know something, you just treat it as a variable. And so here we can say that sigma is not going to be known, but it's going to be something that we invert for. It's going to also be an unknown. And you see that because it normalizes this function here, it's also going to be a weight that is given to this particular data set. And now, if we invert different data sets, and we don't know which weight we should give to these different data sets, this sigma is actually the weight that is given to different data sets. And so by inverting for sigma, we will let the data decide, or the data tell us what's the relative weight that we should give to different data sets. And I will come to that lately. Okay, so this is the likelihood distribution. And we can use, and of course you see that as we add more and more and more parameters, we decrease the level of data fit, and we increase the probability of this. So this distribution is going to be maximized when you have a lot of parameters. So there is nothing to prevent us yet to go to a lot of model parameters. And to do that, to penalize over complex model, there is the prior distribution. So in a Bayesian inference, you know that we combine this likelihood with the prior. And I'd like to show you here how we can use this prior in a transdimensional framework to prevent us to go to too complex models. And for that, I'll use a cartoon again. So here, this is the prior that is going to, the prior represents what we know about the model before looking at the data. Let's imagine we have just one model parameter. We just invert for x1, a constant. And we want to put a prior on this value. Let's assume that we are going to use a uniform prior. And so this is a prior distribution on the x1. It's a distribution, so it needs to integrate to 1. So if we have, if the minimum and the maximum value is like x min and x max, the range of possibilities, delta x. That's the range of possibilities for my prior. So that means because the integral of this function here, the uniform function, needs to be 1, the probability of a single model is going to be 1 over delta x. So then the area, the blue area is 1, right? And now let's see what happens if I add an extra parameter. Now we are in a two-dimensional space. We change dimension. We still have a prior. Now we are in a two-dimensional space. We have a prior which is also uniform, delta x, but we have a prior in 2 dimensions. And the integral also needs to be 1. So that means, so for the integral to be 1, that means here, the volume here, this volume needs to be equal to 1. So then that means the probability of a single model is going to be 1 over delta x squared. So you see that as we increase the range of possibilities, we add a dimension, we increase we are happy because we are able to fit the data better. But in the same time, we also increase the range of possibilities. And so because all possibilities are equally probable a priori, the probability to have one possibility is going to be lowered where we increase the volume. And so this is a way to, I guess, implement this concept of a natural parsimony that says that between two models, two theories that fit equally well the data, the simplest one should be preferred and should be more probable. And so here is an example. Here we have two models. There are x0, maybe it's like a value, a number. The density is equal to 3. And here we have one model where the density is equal to 3. And here we have another model where the density is equal to 3, to 3, to 3, to 3. So it's exactly the same model. But on the top, you have a model that is described by one parameter, and on the bottom, you have a model that is described by 4 parameters. So that means here, a priori, the simplest one is more probable, right? So you see that how the prior distribution is going to penalize over complex model, whereas the likelihood distribution wants to have a complex model because it wants to fit the data. So that's it. And then we have a distribution, the posterior, which is a transdimensional distribution. It's going to be very complicated because it's not analytical. It's not differentiable. You cannot differentiate when you change dimensions. And so here is a very naive representation of this distribution. We have, in a two-dimensional space, we have a distribution in a 2D. But actually, in reality, it's a distribution that also exists in 3D and 4D, and you can change dimensions. So it's a very complicated distribution. But for any point here for any value of x1 and x2, we can compute the value of this function. And this is our solution. And that's it. That's finished. The solution is just given by this. The m, for any given m, for any dimension, you can compute the Posserer value. And now the problem is, how do we look at it? How do we approximate it? And the most simple way to do that is what we have seen with Andreas, with Klaus, is like a Monte Carlo, Markov chain Monte Carlo algorithm, the Metropolis algorithm. We can sample this distribution. So here again, it's the same. Here it's a cartoon. It's a distribution in 2D. But the goal is to try to sample this distribution. And it's a transdimensional distribution. The number of dimensions is variable. So we can use a Monte Carlo algorithm with the transition, proposals, everything. Then now you know about that. It's perfect. And the solution is going to be just a very large ensemble of points in this transdimensional space that are distributed. They have a good property. They are distributed according to the solution. So our solution is going to be that, an ensemble of points with different dimensions. And of course, from this ensemble of points, we can derive statistical properties. We can look at integrals. We can take the mean. We can take the median. We can do a lot of things. Here, for example, we can look at integrals. And if we are interested in what's the probability of x1, we have a distribution here for x1 and so on. Okay, so now if we apply that to, we go back to our regression problem with paleoclimate data, we can apply that, and the solution is just going to be a lot of models like that, a very large ensemble of models, a lot of black models. Some models here have 2 layers, some have 6 layers, some have 10 layers, and there is with the Monte Carlo algorithm, we just have sampled this space, this transdimensional space. And that's the solution, and we're done. And the problem is that it's very ugly. Like we have a large cloud of black models, and it's very difficult to look at and to interpret because it's a big distribution, and so we have to make an effort now to extract information from this distribution. And one thing that we can do, and that may make sense, but it's a choice, we can look at the mean value here and the credible intervals. And so you have a mean value in red of the models as a function of time or depth. Yeah. And so you see that the smoothness of this curve in red here, it doesn't depend on any smoothing that we have applied in advance, any regularization, but it's a smoothness that is given by the data. And now if we were interested in where the discontinuities, the change points, and how many change points we have, we can look at the distributions. We can look at the distributions of each time there is a change point. We can look at the histogram of change points. And so this is the probability to have a change point at each location. And if we were interested in the number of change points, here we have a distribution over this large ensemble for the number of change points. And you see the most probable number of change points is 3. But you have also a lot of models with 4 change points. You have also models that fit very, very well the data with 20 change points. But those, they're actually down-weighted by the prior because they are in a space that is very, very large. So that was an example with a regression problem. And you see that how the solution is a large ensemble of models in a transdimensional space. Now I'd like to show you also another example. This is also a regression problem, but this is now we are trying to fit a polynomial. And the question is, from this data set, here we know the noise, should we fit a constant or a linear function with 2 parameters, or maybe a cubic function with 3 parameters, or a quadratic function with 3 parameters, sorry, or a cubic, or so on. We don't know the order of the polynomial that we would like to use. And this is we can sample this distribution, and this is a movie that Rhys Hawkins, who's now at ANU, has done. And here is the sampling, a movie where you see that we are trying a lot of different functions to fit the data. And so here you see that that's the probability distribution for the order of the polynomial. So here constant is very poorly sampled. And so here we have a linear function and a quadratic and a cubic function. You see that the most probable function here is a linear function. So we didn't have in advance to say, oh, I want to fit a linear function with 2 parameters. The number of unknowns was variable, and we recover a solution that we can represent that way. Okay, so that was a way a bit to introduce in a simple regression problem how do we apply a transdimensional inference. Now I'd like to show you before I finish, some applications to seismology. And the first most obvious application is receiver functions. Because inversion of receiver function for a 1D model. So this is a very classical problem in seismology. We want to recover a model of the Earth below, a 1D model of the Earth below a station. And the data that we have, there are body waves, the vertical and the horizontal component of body waves. This is the P arrival. And after the P arrival, you have a lot of different wiggles that are due to conversions and the reflections at discontinuities. So these data, they contain information about the discontinuities, and we want to recover a 1D model. So we can do that, and from the data, we can recover a large ensemble of models. Again, an ugly cloud of models in black here with different dimensions. We can produce as many as we want, as long as we have time for that. And we have a lot of models, and we can now look at the statistics of this model. We can look at them as a density plot, for example. This is the ensemble of models. And we can look at the mean value. We can ask, what's the probability to have a discontinuity? And so here, instead of having a solution where at each depth we have a velocity value, we have actually at each depth a full distribution that might not be Gaussian on the velocity value. Okay. And so now what we do very often also, these receiver functions, we combine them with surface waves. And so those are two different data sets. We often like to combine body waves and surface waves. They are different frequency bands. They are difficult to combine to try to recover a 1D model. And so now the question is, when you have two data sets of different nature, with different sensitivities, associated with different uncertainties, how do you combine them? And I'd like to show you here that we can do that again with Bayesian inference by letting this sigma, the error in the data, be an unknown. So now instead of D, we have 3 data sets, for example, D1, D2, D3, and they have very different data sets. If they are independent, we can write the likelihood here as a product of the 3 likelihoods. The likelihood for the first data set times the likelihood for the second data set, and so on. And so here, each likelihood is going to write like that. And you see that this sigma for each data is going to give the weight that we give to each data set in this joint inversion. So by letting the sigma be an unknown, you don't have to fix the weight into advance, but we let the data recover naturally the weight that is given to each data set. So here we can combine together different data sets, and so we have done, so this is an example of application where we are combining surface waves and receiver functions to recover the structure of continents. And we see that the cratons in Canada and India, the oldest continents, they are quite similar, and we can actually use this type of methods to discover new things about the structure of the Earth. So I'll move on now. So now, so those were for 1D problems. Now the question is, how do we do that for seismic tomography because changing the number of layers is easy. You can add one layer, remove one layer, but in 2D and 3D, when you want to change the parametrization, how does it work when you add one cell, remove one cell? You have to remesh each time, and this is a difficult problem. So that's why the parametrization is quite important. We need a parametrization that can be adaptive. And so that's why we use Voronoi cells. And Voronoi cells are a way to parameterize the Earth that is quite useful because you just have to define the black dots here, and the velocity is going to be constant in each cell. And the mesh here, the blue lines, that are just perpendicular bisectors between each pair of points. So here, the unknowns in the problem, what we are going to invert for now, is going to be the number of cells, the number of black points, the velocity value associated to each cell, and of course the position of the cells. So for example, if there is a lot of rays in one side, we may want to have a lot of small cells in this area. If we lack information in one area, we'll have a large cell there. But we don't decide that in advance. That's part of the inversion process. We let those parameters, they are unknowns in the inversion. So it's fun because yes, these Voronoi cells, they have a lot of very nice properties, and you find them everywhere in nature. They have universal properties. You see them in turtles, in giraffes, and numerically they are very convenient to work with. Yeah. So let's see how does that work with a synthetic experiment. We have a model of the Earth. This is what the target model. That's what we are trying to recover. This is our ray geometry. As opposed to what Andrew was showing here, we are placed ourselves in the worst case scenario where the ATA is going to be very hill-posed because we want to challenge the algorithm. So for example, we put on purpose a lot of rays that are parallel. We know it's not good, but we want to do that to see how the parameterization is going to adapt for that. So we use the worst ray geometry, the worst design, to see if the parameterization is going to be able to deal with this problem. So we expect a low resolution in this area. We put a lot of information in one side and not a lot of information in the other side to see if we are going to have small cells in one area and so on. So the solution, again, is going to be an ensemble of millions of models that are like that are Voronoi models. Some are complicated and fit the data. Some are simple and have a high prior probability, but the solution is a large ensemble. And this ensemble, again, it's ugly because you have discontinuities, the parameterization, there is no smoothing, the parameterization is a bit coarse, but we have this large ensemble, and we can look at this ensemble statistically. And one very easy thing to do is just to take the average. We can just stack all these models. And because the parameterization are changing, when you stack the models, they are going to, the average is going to be smooth. And so this is a smooth average. And you see also that when there is discontinuity that are really required by the data, all the discontinuities that are in the individual model, they are going to constructively interfere, and you can actually recover a discontinuity without having to do the smoothing. And another thing is that each pixel, you can take the average, but you can also take the standard deviation. And the standard deviation is going to be a measure of uncertainty on your model. So here we have a way with a Bayesian inference to keep this information about uncertainties, and we have been able to propagate uncertainties from the data towards uncertainties in the model. And you see that when there is a sharp discontinuity, there is high uncertainty because we don't know where the discontinuity is exactly. Yeah.
So on those bottom images, there's an underlying grid that you interpolate the different Voronoi grids to?
Yes, but it's arbitrarily small. Yeah, you can. Yeah. So here you have Voronoi cells, and they are real numbers because they are defined by the centers, and then you just stack them on a small grid. But this small grid, you can make it as small as you want. It's just a way to project the models. And so for comparison, this is a comparison with the same data set inverted with a more classical method where you have a 20 by 20 grid and where you apply regularization You have different solutions. On the horizontal axis, you change damping. On the vertical axis, you change smoothing, and depending on the regularization, as expected, we get different solutions. And there is a smoothing, so we don't get that much the discontinuity, and we see the smearing here that we expected. Whereas here with this, with the transdimensional solution, we get something that where we can recover better the discontinuity. Okay. I'm just checking the time. Okay, and I'm going to show a couple of applications, and then I'll be finished. Here is an application for ambient noise tomography in Southeast Australia, where we have 3 different data sets of very different resolutions. And this is, again, a design. So that was a question I had for Andrew. Here, the design here is just a regular grid. But is the regular grid the optimal design for ambient noise tomography? I don't know. Yeah. So, OK, but anyway, that's the data that we had. And then we want to perform tomography on that. And we want to have different resolutions. And so this is the work of Simone Piglia. And he showed that actually with this type of approach, he was able to show that you have structures that are linking the island of Tasmania to the mainland Australia. Yeah. Now, okay, another example for the full US array, and this is what Scott Burdick and Vedlekic in Maryland have been working on. The idea was to do travel time tomography for this full US array, this super nice telescope that we have in the US. And the solution is an ensemble of models. So this is a 3D tomography. And and we have, here is a movie for all this, and this is also what Klaus was showing. We need to, this is what Albert was saying all the time. We don't need to look at an average value. We don't want to look at individual models. We just want to look at a movie of a lot of different realizations. So you see all these Voronoi cells, they are a bit discretized. But but there is a lot of statistical information there. And so, for example, you take the mean of this model of the US at 200 kilometers, and you see that. And at each point, there is a full distribution. Here is the mean, the uncertainty, and this is the full distribution at each pixel. And so here you see they have built a 3D. A full 3D tomographic model, which is probabilistic for the US, and that can be useful. A last example, this is towards global tomography. This is again the work of Rhys Hawkins, where he's trying to build actually a global tomographic model from surface waves. And without regularization, we expect to have larger amplitudes, and because we are not damping or smoothing. Okay, so to conclude, I would say that what I wanted to present is a different way to perform tomography, where we don't regularize. The downside, of course, I guess you have understood as well, is that we use the Metropolis algorithm. It's very long. We have to produce a lot of samples. It's not efficient. So for small problems and big computers, it can be nice, but we are still challenged by the computational power. And so, yeah, before I finish, I also wanted to say something about this problem of having a large distribution that we are not able to exploit. And for that, I have an example that I'd like to show. Is an example, so this is a fictitious example. Let's assume that we want to predict the weather tomorrow, and we are in a 2-dimensional space. The question is, what's the temperature going to be tomorrow, and what's the rain the precipitation going to be tomorrow? And so we want to have a point on this 2-dimensional space. And one way to communicate this forecast is very simple. It's just to give one point in this 2-dimensional space, is to say, okay, tomorrow the temperature is going to be 20 degrees, and the rain is going to be at this number of millimeters. And this is very easy to convey as an information, because it's just 2 numbers. You can explain that to a kid very easily. You can say tomorrow it's going to be hot and it's going to rain, and it's very simple. But at the same time, it's not very good because you don't have uncertainties on that. And you want to be, if you want to be a bit more like rigorous, you want to add uncertainties. And so if you add uncertainties, it's better in the scientific way because you say, okay, the temperature tomorrow is going to be 20 degrees plus minus 1 degree and same for the rain. But in the same time, you have now 4 numbers to give. You have 2 numbers for the temperature, the mean and the standard deviation, the mean and the standard deviation for the precipitation. So you have to talk about 4 numbers. The level of knowledge is more accurate, but at the same time, you have to give more numbers. It's more difficult to visualize and to communicate. You can go one step further and you can say, okay, actually it's a Gaussian distribution with a correlation. Now you have 4 more numbers because you have a covariance matrix. And if you want to explain that to a kid, you have to say, okay, I don't know exactly if tomorrow it's going to be hot, but I can tell you that if it's hot, it's going to rain, and if it's cold, it's not going to rain. So the message, it's more complicated. So you see, as you increase your ability to express the level of knowledge, in the same time, you decrease your ability to communicate and to describe what you're having. And this is really a problem. And for example, and here we are in a 2-dimensional space with 1 Gaussian in 2 dimensions. It's very easy. But we could, now we have 2 Gaussians. Quite easy in 2 dimensions, but this is quite difficult to express for a kid to say, okay, what's the temperature and the precipitation going to be tomorrow? Yeah. And actually, when we do Bayesian inference, we are in the case where we are sampling the full distribution. And we are very happy and very proud because we say, yes, we have a full distribution, the full state of knowledge, the full uncertainties. But in the same time, we feel a bit alone because we don't know how to communicate that. And if we have in a 30-dimensional space with a full distribution, we don't know what to do, and this is very difficult. So there is this paradox as between the ability to visualize and communicate and the ability to express to quantify the level of knowledge. And for example, let's assume if this is the depth of the moho and the density in the crust, it's going to be very difficult to say that to a geologist, okay, the depth of the moho and the velocity or density in the crust is just this. And what do we do with that? It's not easy. But then, anyway, what I wanted to show you here is that when you look at a model, a tomographic model here, like that, you have to remember that what you're looking at is just 1 point without uncertainties. We're stuck here still in global seismology, and it's important to remember that. Yeah. Okay, I'll stop here. Thank you.